Okay, so more generally, a special case of 2-qubit gates are those 2-qubit gates that can be written as products of single-qubit gates. So with a node by AB, the 2-qubit gate that applies A on the first qubit and B on the second, where A and B are some single-qubit gates. So for example, XH applies X on the first qubit and H on the second. And in a quantum circuit, we represent this as follows. Simply X on the first wire and H on the second. And so in particular, as an example, the 2-qubit gate XH acts on the standard basis as follows. Okay, let's look at the first standard basis state. So Ket0, 0. The first qubit maps to X applied to Ket0, and the second qubit maps to H applied to Ket0. So all in all, we have Ket1 on the first qubit, and then 1 over square root of 2 Ket0 plus Ket1 on the second qubit, which you can then expand out to write as a superposition over the standard basis states. Okay, so here is one exercise for you. So compute the state HH applied to Ket1, 0. So Hadamard on both qubits applied to Ket1, 0. Take a moment to pause the video if you'd like to do this exercise, and then you can come back and I'll show you the solution. So we are asked to calculate the 2-qubit state HH, so Hadamard on the first qubit, Hadamard on the second qubit, applied to the state 1, 0. Now the rule is that this is equal to the product state, which is in the first qubit H applied to Ket1, and in the second qubit H applied to Ket0. I'm putting parentheses to be very explicit about this. And now we can just substitute the values of H applied to Ket1 and H applied to Ket0. And so we obtain 1 over square root of 2, 0, minus 1 over square root of 2 Ket1 for the first qubit. And for the second qubit, we get 1 over square root of 2 Ket0 plus 1 over square root of 2 Ket1. And now we can expand this out and write it as a superposition over the 4 standard basis states. As usual, we apply this distributive property. What we get is for the 0, 0 term, 1 over square root of 2 times 1 over square root of 2, so 1/2. For the 0, 1 term, we're multiplying this times this. So again, we get 1/2, 0, 1. For the Ket1, 0 term, we're multiplying this times this. And so we get minus 1/2. And for the 1, 1 term, we're multiplying this times this. And so again, we get minus 1/2. And so this is the resulting 2-qubit state. Now, one important remark to make is that not all 2-qubit gates can be written as a product of 2 single-qubit gates. An example of this is the CNOT gate. This cannot be written as a product of 2 single-qubit gates, and I encourage you to try and think about why this is the case and to prove it on your own.